Hi guys, in this video I'm going to cover a complete example of mediation. You'll notice that my channel has several examples of mediation. This one is going to use the quant-sci package in R, but you can also do this completely by hand, so to speak. And I have another more recent video on how to do this in a very similar way to SPSS's process, where you'll use bootstrapped confidence intervals. So this one is a little bit easier to do because quant-sci kind of takes care of a lot of the stuff for you. But if you really wanted to dig deep into mediation and have more control over it and do something other than a very basic model, I've got to recommend you watch one of our other videos that covers how to do this with bootstrapping. But for my class, let's talk about mediation. So we're going to cover the traditional Barron and Kinney steps because it helps as a good base for learning more about mediation. But there are a lot of modifications to this procedure, including bootstrap confidence intervals to look at the indirect effect. There are lots of R plugins. Kinney's even got some stuff on his website. So I've given you some places to go and expand. If you're not in my class, I would recommend looking at the bootstrapping options. But here we go for my advanced statistics course. So the traditional steps, so there's you really should call these stages, because I don't want to confuse this with hierarchical regression, because that is not what it is. Okay, so this is going to be 3 simultaneous regressions, 2 of them simple, 1 of them multiple. And so what we'll do is we'll first show that X predicts Y. Essentially the X and Y are correlated, and that's called the C path. Then we're going to show that X predicts the mediator, or M, and that's the A path. Okay, this is not to be confused with B, as in the letter B representing coefficients. These are just called A, B, and C because they are. But after we show that X predicts Y and X predicts M, what we then want to do is show that M predicts Y, because what we're really doing is setting up a 1 to 2 to 3 scenario where X predicts M and M predicts Y. And therefore, then X to Y is lessened, because instead of going straight from X to Y, you've taken the detour and gone from X to M to Y. So remember that mediation is all about that third variable, a third wheel problem, where the relationship is actually X to M to Y rather than just X to Y. And we're going to show that M predicts Y while also controlling for X. And then we're going to show that that C path is lessened. Usually that means closer to 0. So you have to be real careful when you're watching this here, because the Sobel test can be positive, it can be negative, it doesn't really matter. But you want to make sure that your C to C prime gets closer to 0, the relationship is lessened, because if the relationship is increased, something else is going on. And that's usually an interactive effect. But you don't want to just like randomly pick, oh, I'm going to do mediation, oh, that didn't work, let's try moderation, right? See, these are the theory-based analyses. But when you see that C gets bigger, further from 0, remember that more negative numbers are smaller, but they are bigger in strength, then that implies that maybe it isn't mediation. Right. So we'll also use the Sobel test to determine if C and C prime are different. And the way you determine if C and C prime are different is if the A-B combination is better than 0, which seems a little odd, but essentially you're testing if the effects have been redirected through A and B, which remember are the X to M and M to Y paths. Okay. So we're going to use dataset 6. I believe this is from Hayes' book. And I made up a different example to go on top of it because the example from the book is kind of boring personally. So we're going to talk about baseball. It's almost baseball season here. It's the end of football season. We got to suffer that small amount of basketball, and we'll move on to baseball season. So it's going to be the American League or the National League, right? It's going to be our IV, which is going to be X here in this example. Our mediator is how much money they have for pitching, because it can all come down to pitching. And then a DV is the extra innings of pitching relief. So how much extra do they have to use? So their main pitchers and the relief pitchers, essentially, we're kind of measuring how many innings we're going to need because our main pitchers are done, or whatever. Right, so we're not really measuring extra innings. We're measuring how much relief pitching do you need. So does that budget that we have. Mediate the relationship between the league and the innings. So if one league uses it more than another, does the budget mediate that? So if I have a big budget, I can take my pitcher out because I have extra ones on staff. So mediation power I find to be real tricky in the sense that it's not always super clear because you're trying to actually predict no effect, which is like never a good thing because then you have to use thousands of people. So you kind of want X to originally predict Y, then you want to predict M, and you want to stop predicting Y, and then you want M to predict Y. So I would estimate the effect size you'd have for X to Y originally, X to M, and then M to Y, and pick the smallest one that you think has the effect. So the original X to Y correlation, the X to M correlation, or M to Y with X in the equation, and use that as your effect size to estimate here. There are R plugins, but honestly this will work just as well for you. So we're going to use G Power. Okay. All right, so we're going to open G Power here. And what we're going to do is use t-test and then linear multiple regression, fixed model, single regression coefficient. Now we could use the R² version as well if you aren't sure, but essentially what we're doing is testing if one of these regression coefficients is better than 0. Okay. And so this one, linear multiple regression coefficient, I'm going to click two-tailed test because that's normally what we do. Determine for our effect size, and then direct. So you could pick partial R², which is PR², or you could, since there's only one predictor normally, unless you're doing X, M to Y, right, then there's two predictors. Here you could pick whatever number you're kind of used to for effect size. So my example here, I've done a medium effect size, so 0.09. Okay. Transfer, calculate and transfer to main. 0.05, 0.80, and then the number of predictors depends on which one you're picking. So I have an example here. From X to M, you'd use one predictor. From X to M and X to Y, actually. And then for M to Y, you'd use two. And you pick the one that has the lowest effect size. That's going to require the most people. So in this example, I picked a medium effect size and picked the M to Y relationship, which is where X is in the equation as well. And I'm going to hit enter. And so I need 82 people. That's perfectly reasonable. All right, in this example, I'm actually going to run through a complete data screening and work through data screening, including the extra outliers component. So if you aren't familiar with our data screening process, you should go back and watch some of those videos, especially our regression videos that talk about hooks and leverage some more. So let's import that file. I'll run a summary of that and make sure that I have everything cleared up. So the league here is factored. I know there are not this many teams. This is made up data. Well, it's real data with a fake example on top, but just pretend like maybe it's a bunch of games. So instead of teams, we've got games here. Innings here runs from 0 to 30. Okay, that's good because I know that I can't have negative innings. 30 innings is probably above the maximum what we've ever had, but let's just play along here. And our budget here runs from 0 to 20, and we could say maybe that's in the millions. Okay. Oops. Okay. And those can't be negative. Now, the upper numbers might not be accurate, but again, it's just an example for fun. Okay. I can see that from my summary function, I don't have missing data, and I only have 3 columns anyway, so I can't really estimate missing data using mice because I don't have enough columns. And to get our data screening procedure here, we're going to run our final model. So we're going to screen all of our variables. In a mediation model, we're going to run all of the variables together. So that specifically is going to include the DV is predicted by, so tilde, X and M together. So what we want to do is say that budget here, which is our dependent variable, is predicted by both X and M, and it's in our original data set. And this is just to get the assumptions checks we're interested in. So I'll run that. And you'll notice I don't have a summary here because I'm not actually looking at the summary of this model yet. I'm just looking for outliers. All right, we're going to check for Mahalanobis. So our outlier procedure is going to involve Mahalanobis, Cooks, and leverage. So we're going to do a 3-part check, and this is a baseball example, so I can say 2 strikes, you're out here. If you hit on 2 of our outliers, we're going to exclude you for being too influential on the slope. Okay. And so this section here kind of walks you through how to do all of this, but the interesting thing we're going to do that's sort of different than my other data screening procedures is we're going to save those scores, and we're going to save them in a weird way. So normally we just use a summary and we see how many people's scores are less than the cutoff, and if you're not less than the cutoff, you're a bad score. What we're going to do here is translate people who are higher than the score into numeric codes. So what R does is when you use this sort of code, Mahal is greater than our cutoff score, this is going to be a true-false answer. So people either are greater than the cutoff score or they are not. As.numeric changes that into a number. And so we want to code people as a 1 if they're an outlier and a 0 if they're not an outlier. And we're going to use that to find 2 strikes, you're out. So what that will do is it will save all of them and we'll kind of add up. So we're going to code everybody who's an outlier as a 1, everybody who's not an outlier as a 0. This is a little different than what we did for ANOVA, because in ANOVA we were just making sure on just Mahalanobis or just z-scores. But now we have multiple indicators, and so we're going to save them and then kind of tally them up. All right, so for our Mahalanobis function here, we're going to do the master data set, but I've got to exclude leak because it's a categorical variable and it will not run with that. Our cutoff score, we're using the big important rule, is 0.001. And we're going to use the degrees of freedom is going to be 2 because it's 2 columns that we're using. And so that cutoff score is 1382. And our bad Mahal is the number of people who are the people coded as 0s and 1s. So let me just type that over here so you can see it. And so it looks like we only have 1 outlier, but that's hard to read, especially if you have thousands of data points. So I'm going to make a little table here. And remember that 0 is good and 1 is bad here. So this is a little backwards from what we've been doing before. All right, the way leverage works is it looks at the how much influence a person has on the slope. K is the number of predictors, which is 2 in this example. X and M. This is where we're going to use that output that we saved a minute ago. And we're going to use the function hat values to calculate leverage. The cutoff score is 2k plus 2. Keep those parentheses, or R will do the order of operations that you don't want, divided by the number of rows in the data set. So we're going to calculate our cutoff score by entering k. So basically you don't want to change the code here too much. You just want to enter what k is. And we're going to do the same procedure as we did with Mahalanobis and calculate the number of people who are above that cutoff score. So you can just change k and then leave the rest alone here. So our cutoff score is 0.06 if I round up. The number of, we've calculated the bad leverage. So this is just a giant vector of people, and there doesn't appear to be any 1s, but let's just check that using a table. And nobody has any influence on the slope. So pretty much no outliers for leverage. Same idea for Cooks. Cooks is a measure of influence and discrepancy, so influence on the slope and how far away you are from the rest of the data. The function for that is pretty easy, cooks.distance. The formula is 4 divided by n minus k minus 1, that's degrees of freedom on the bottom. And so we're going to use in row from master to give us the number of people, minus k, which is 2, minus 1. And we should get a cutoff of around 0.04. Now, one way you can tell you're doing this correct is that Cooks and leverage will be close. They'll both be small decimals. No negatives, no big numbers. Okay. So my cutoff score for Cooks is 0.04. The number of people who are bad is 4. So I have 1 Mahalanobis outlier, no leverage outliers, and 4 Cooks outliers. Now what do I do with all of that? Well, now I'm going to add them up. So my total outlier score for each person, I'm just going to add all 3 of them together. I'm going to create a table of the total outliers. And so we've got one person who has, okay, so remember on tables here, this is the number. So they have 0, 1, or 2 because we added up. And there are 105 people who have no outlier marks, 3 people who have 1 outlier mark, and 2 people who have, 1 person who has 2 outlier marks. And so we want to get rid of everybody who's got 2 or more marks. So this is 2 strikes, you're out. And so we want to say subset out the data set where the total number of outliers is less than 2. Okay. There's no good citation for that rule. I've just found it works really well, so it's not as sensitive as either one of those things individually. So sometimes cooks and or leverage can be fairly sensitive. Mahalanobis is not so much, but if we have all 3 of them, we can say, well, they marked on 2 of them, so we excluded them. Okay. All right. So the point of mediation is that there's a lot of correlations going on. So it's kind of a test of suppression is essentially what this is. And so we want them to be highly correlated because that's kind of the point. But we still want to check and make sure we don't have perfect correlations or this isn't going to run. So I'm going to subset out and clear out that 1 bad outlier. And then I think it looks like I skipped this step, but you could also look at correlations here by examining core on the data set. So I could save this as coral. I've done this before, right? Core of my master data set, but we're going to drop that first column because it's categorical and use the symbols for numbers function. Fingers got ahead of myself. Of our correlation. And we have a little dot here, meaning it's between 0.3 and 0.6. But basically, if you're not including other variables, you might just skip this step. Okay. We're going to run the rest of our assumptions, but no fake regression this time because it's real regression. And so we're going to create our final model again, this time on the no out data set. So I changed out the data set name is the other thing I did. And then I'm going to set up my assumptions like I normally do, except this time I don't have to do any of that fake randomization stuff. So I'm going to get my studentized or standardized residuals. I'm going to standardize my fitted scores. And now I've got predicted scores versus error. And we standardize those to make the whole thing easier to read. I'm going to check out my histogram here, so we should all get the same picture since there's no randomization. And it's a little wonky because while most of the data is centered here over 0, it's like really tall over here and then nothing over here. So data is a bit skewed. And it's pretty linear. I would say the most of the dots are fairly close to the line. The fact that it's above and below is a little problematic. But I would say, well, when you make it bigger, it looks worse. So this is starting to become slightly ogive or S-curvy, and that's not very good. Okay. Probably because it's got categorical predictors in it. That always tends to screw things up. For homogeneity, it's okay. It's mostly 2 to 2. Got 1 or 2 little buggers out here at 3. And then for homoscedasticity, it's actually fairly square. So the spread here is a little larger than the spread here, but I don't think it's anything terrible to worry about. Okay. All right, let's go back to Word here. I'm gonna scroll through all this. I said it's not very linear. It seems to be okay. So now we're going to run these regressions and kind of check one step at a time to make sure that our requirements for mediation are met. So we're going to run that C path first. I'm using X to predict Y. So I'm going to call it model C. And I just fill in Y, or the DV is predicted by X here. So for model C, I've got innings is predicted by league. And I see that that is significant. Okay. And so the interpretation here, since league is a categorical variable, is that there are a difference in the number of innings that people are having to pitch. So the innings pitched is different for each group. Okay. Let's go back to Word. Okay. And so is that C path significant? Yes. So I have B. I filled in B here under estimate. T, 106. Where the heck did I get 106 from? It's right here on the second degree of freedom for F equals 2.73. That's under here under T. P equals 0.007. So we can put those model statistics in a table. So I can give you my overall model too. 1 and 106 equals 7.43. P is the same, 0.007. And then R squared here under multiple R squared. Now, I don't know that you really need to report both of these unless you're answering a class question, because they actually tell you the same thing since we only have one predictor. For my A path, what I'm going to do is use X to predict M this time. So it's the same model, we're just switching out Y and M. So run that bad boy. And it's also significant. So what we want to do, I'm scrolling past everything, B is 2.11. So league predicts budget as well. So there's a difference in budget in millions for these two leagues. 106 here is from this number right here. 3.22 is from right here. 0.02 is from right here. And I could write out my F statistic, but again, it gives you the same information. The nice thing about the F statistic is that I have multiple R squared, and so that gives me my effect size. And remember, when you only have one predictor, that's the same thing as PR squared. Now B is where everything gets kind of tricky. So for path B, which is the mediator predicting Y, and path C prime, we put them in the equation together. So we're going to have X plus M, and use that to predict Y. So this is actually a multiple regression, but a fairly simple one. And we're going to use those two together, because the interpretation is that M predicts Y controlling for X. Okay. And so I should see this output here. I have it pasted over here so we can read it a little better. So is the B path significant? So we're looking at budget here. So B is 1.56. So our budget predicts the number of innings that a pitcher might pitch. And the T statistic actually here should be 105, small typo. So the number is pulled from right here. 4.64, P less than 0.01. The overall statistic here is 2 and 105. It's 1522, P less than 0.01. R squared is 0.22. Okay. So B is significant. So C has been significant, A is significant, B is significant. All right. What about C prime? Is it closer to 0? Okay. Now, it's the same thing as model B, but now we're just going to look at the other predictor. In a perfect world, you'll see this, people list this as fully mediated. The terminology is kind of slowly washing out, or partially mediated. We're more interested in the indirect effect and its confidence interval. But if you're sort of talking about tradition, X is now going to be non-significant. But even if it's not, we're going to still see if C is closer to 0. Since this is a book example on mediation, it is non-significant, but there's still a pretty good difference here between number of innings pitched between leagues, okay, right? Because we're predicting innings right now. Okay. But I would type all that one up. 347, 105, -106, P is 0.15. Okay. The model statistic is the same, so don't repeat it. Now, how do I know if the C and C prime are different? Our original C value was -676. Our new C value is -3.46. So it halved. But is that halve important? What we're going to use is multi-level. I lied to you. Quant sci is moderation. We're going to use the multi-level package actually to calculate the Sobel test. And the function is Sobel. And the way that Sobel works is that you come over here, all this stuff about Sobel, and you put an X, M, Y. So be sure you put these in the right order or you're going to get the wrong test. And so we're going to put in X, comma, M, comma, Y. And essentially the Sobel test tells you if C and C prime are different. And really you want to make sure that C is closer to 0. All right. This will also allow you to determine if you did this first 3 steps right, so stages right. Okay. So we've got X, M, and Y. Under my Sobel test here, it actually, I know I just made you walk through all those models, but here they are, 1, 2, 3. you don't get the F statistics. So just kind of can check, make sure you've done this right. So here's Y predicted by X. So this is the C path. Y predicted by X and M. So this is the C prime path, and then B. And then we've got our M predicted by Y. This is A down here. So the order is not the order of the like normal stages, but it kind of tells you what's going on here at the top of each part. Okay. So remember that X to M is A, okay. X to Y given M is C prime, M to Y given X is B, and X to Y is C. The more fascinating thing here is that indirect effect, so we're going to report that. Now you'll notice that the indirect effect is C minus C prime, but it's also A times B. So we can look at either one of those to get it. We get the standard error of that indirect effect. That gives me a Z value, so it's testing if the difference between, if the indirect effect is greater than 0, or different from 0 rather. And I have to take this Z value and figure out if that's significant. So kind of scroll through all of my giant text here. So we're going to report that Z value and figure out P for our Z. We're going to do that for Znorm. And I'm going to fix this because it is incorrect. So we're going to take the absolute value of our Z score. Because if it's negative, we want to, if it's negative or positive, we want to make sure we always get the same number here. We want to multiply that by 2 to get a two-tailed test. Because in this particular example, I did lower tail equals true to account for the fact that it was negative, but you'll see that I fixed my code over here, but not fixed my document. Okay. So I'm going to just save that as save. It's the exact same line as this one, so X, M, Y. And I did actually lower tail equals false. It doesn't matter as long as you do absolute value. In this case, actually it does. If I do the absolute value, that always makes it positive, and so we want just the tippy top tail, and we're going to multiply that by 2. So be sure you do it this way, and I will fix my Word document here. So it tells me that the Z-score for 2.65 is 0.008, which if you're familiar with Z, remember that 1.96, two-tailed, is 0.05. And 2.5 something. I haven't taught intro stats in a while, clearly. 2.56, 2.52, I don't remember. Anyways, 2 point something is 0.001, so this makes sense here. Okay, so it's 0.008. Okay. And we're going to change this bad boy to F here, just to make sure that we all do the same thing. Ooh, what happened? All right, so significant mediation occurred by including budget between league and innings. Okay. And let's interpret everything. Remember that the variable is dummy coded, so I can use tapply to calculate the means for each one. And the AAL needed more pitching innings of relief. And that's not too surprising if you believe the National League has better pitching. Right? If I look at league predicting budget, it appears that the AAL is spending a lot more money on pitching. And that might be because of the Red Sox and the Yankees. Okay. Budget predicts innings, and that's a positive and continuous effect, so that as your budget increases, you have more innings of pitching relief, because you can afford it probably. And when we put in budget, the effect between league and relief kind of dissipates, so it gets smaller and closer to 0. So what's happening really is the league has different budgets, which allows them to control their relief pitch innings. Generally, you don't make a graph of this. You create these little mediation triangles. And so you could put mine below. Use mine in this Word document and edit it to fit your needs. If you follow sort of the Hayes Guide to Mediation, you won't want to use standardized values because the IVs and DVs are changing, so that standardized effect is not totally comparable. I always present B, so it's in the scale of the data. I've seen beta presented. There's no, reason not to, in the sense that as long as you're clear to reviewers which one you're using. But I think it's best to use the original scale of the data. especially because the IVs and DVs are changing across, versus when you use beta in a normal regression analysis, the DV is at least always the same. And then last but not least, I have an example of what the original example was. It walks through each analysis. It looks like I had maybe 2 outliers. And then here's an example of what a mediation triangle might look like. So all of the statistics are in the write-up here. The B values are just placed on the diagram. And then I always throw my S statistics in a table because they can always tell me to take it out later. And so even though they're a little repetitive, it doesn't hurt. Okay. So all of that's an example of what mediation might look like doing the actual steps in a Sobel test. If you're interested in bootstrapping, I have another video that covers how to get that sort of bootstrapped confidence interval on your indirect effect.